My name is Sandra Dedesko, and I'm with Professor Siegel in the Intelligent Buildings Research Group. I study indoor air quality and microbial proliferation in the built environment. I think it's important because far too often people focus on energy efficiency, and although that's important, I think there should be a major focus on human health and the quality of indoor environments.
My name is Sandra, and I'm a master's student with Professor Siegel, who you all just met. And today I'm going to talk to you about one of our research projects, which is called the Hospital Microbiome Project. And we're basically looking at both microbial communities and building science parameters in a hospital in Chicago. So I'm going to start by talking a little bit about microorganisms in the built environment. So you interact with microorganisms every day. Every surface you touch, like the desks that your coffee's on, is covered in microorganisms. But luckily, most have a neutral, don't be scared, or beneficial effect on humans. However, when we're looking at a hospital environment, this is not always the case. Hospitals are likely to have a high level of pathogens, which pose a huge threat to human health. And these pathogens come from infected individuals that share the same space with other patients with compromised immune systems. And so, as you can guess, this results in a number of infections in hospitals each year, known as hospital-acquired infections. On a global scale, there are an estimated hundreds of millions of HAIs annually. Here in Canada, in 2009, HAIs were ranked as the fourth leading cause of death. We had over 200,000 cases of HAIs and an estimated 8,000 to 12,000 associated deaths. And in the United States, in 2002, HAIs were ranked as the sixth leading cause of death, but there were just under 2 million cases and just under 100,000 deaths in the US. What's interesting is if you look at the risk of getting an HAI in developed countries, Canada is actually ranked as the highest by estimates from the World Health Organization. And then if I show you a map of developing countries, you can see that Canada actually has a higher prevalence than some other locations shown on this map. So this means that HAIs are actually a huge threat here in Canada and throughout the world. And it led our group to investigate the question, does the built environment play a role in does the built environment affect the microorganisms that are responsible for hospital-acquired infections? And so to investigate this question a little more, we started the Hospital Microbiome Project, where we looked at both building science parameters and also microbial communities at a new hospital pavilion at the University of Chicago. So to investigate this, we took a number of sensor measurements in the patient rooms. We looked at 10 patient rooms on 2 different floors, and you can see that we took a number of building science measurements. So the purple diamonds show carbon dioxide measurements in the patient rooms. We also have a non-directional doorway beam break sensor on each of the patient room doors. But what I mean by non-directional is that it only counts the number of times the door is open, but not the direction that it's open. You can see we also have temperature, relative humidity, and light sensors installed in each of the patient rooms. And then we take all of these building science parameters and we compare them to microbial samples that were also taken in several locations throughout. Now, we use the sensor measurements in different ways, and I want to talk about a sub-study within this larger project, and it's a study of human occupants in the patient rooms. And we wanted to investigate 2 parameters. So the first was occupancy, which is the number of occupants in each of the patient rooms. And we care about this because those occupants serve as a source of indoor bacteria. And the second parameter that I want to discuss is occupant activity, which in this case is the number of times the occupants are moving through the patient room doorways. And this is important to us again because it's a mechanism of resuspension. And what this means is that when the occupants walk across the floor, they're going to resuspend the dust that's settled on that floor. And that's known to contain a high level of human-associated bacteria, and in this case, potentially harmful pathogens. So to investigate each of these parameters, we developed 4 methods of estimation based on the sensor measurements that I showed you earlier in the patient rooms. These are our 4 methods: the beam break method, which uses just beam break sensor data; the carbon dioxide method, which uses just carbon dioxide sensor data; also the lagged carbon dioxide method, which again just uses carbon dioxide sensor data but is slightly different than the second method; and our 4th method is the combined method, which uses both the carbon dioxide data and the beam break data. And so we use these methods to estimate both occupancy and occupant activity, and then we compare the methods to a set of manual counts, where we had one researcher, so a master's student in Chicago, that counted people in the rooms over several hours. This figure shows the deviation from those manual count values for each of the 4 methods, and in this case 0 on the y-axis represents the true manual count value. And so you can see that on average, each of the methods, the middle bar there is the median value, produce a very similar result, so they're all valid ways to estimate occupancy. However, after we analyzed each of the methods and these results further, we determined that the lagged carbon dioxide and combined method, these 2 right here, produce the most consistent estimates over longer periods of time, and so we felt they were the best ways to estimate occupancy. And then we also evaluated each of the methods in terms of occupant activity. In this case, we can see that the methods shown with the blue and the purple bars, which are based on just carbon dioxide sensor data, didn't provide much information on the occupant activity occurring in each of the rooms. And that the beam break sensor data, which is the beam break and combined method, that relied on that data shown by these red bars, provided the most information on occupant activity, and so the beam break and combined methods were the best ways to estimate occupant activity in this case. But if you want to investigate both occupancy and occupant activity, we deemed that the combined method is the best way to do so because it produced the most valid estimates of both parameters. And we can use this method to characterize the patient rooms and find valuable information on the similarities and differences between the rooms, which is important to the microbial data that we're going to later compare them to. So I'm going to show you some of the characterization results that I just mentioned. These are the daily occupancy estimates for about 6 months worth of data using the combined method. And what's interesting is that you can see that there's a lot of variation within individual rooms, but also a lot of variation between the rooms. You can see that the median values are all very different for each room, and also the range. The range varies quite a bit in each room. So this is showing us that we can expect to see very different occupancy at different times in the different rooms. And if we also look at the results for occupant activity, we see that there's still variation within the individual rooms, but that the median values in this case are a lot more similar than the occupancy estimates. And this is important to our investigation because we want to see if the occupant behaviors observed in the rooms have a possible relationship or effect on the microbial communities that are responsible for hospital-acquired infections. So going forward, we'll be comparing both the occupant results as well as all building science parameters analyzed to the microbial samples that are currently being conducted to see if there's a potential relationship and if we can better our understanding of how the built environment affects the microorganisms responsible for hospital-acquired infections and also human health and safety.